Okay, hello everyone. Welcome to today's lecture. Uh, so last time we were talking about different components of the microcontroller and how they are connected with each other, and then we also had a simple simulation or animation to see that how a program is executed on a computer. So focusing on the basic ideas, where the basic takeaway is like program counter is responsible for pointing to the next instruction that will be executed, and then that instruction is fetched from the code memory, brought into the processor where it is decoded by the instruction decoder, and then based on the result of decoding, we either read some value from the memory and bring it in the registers, or we add some registers together, which basically mean we perform some kind of arithmetic or logic operation, or we write some data back into the memory depending upon the depending upon the kind of the instruction which is which is decoded. Okay, so that was the point where we left last time. So do you have any questions regarding the previous lecture or the week before that? If yes, please let me know. Okay, if no questions, and again, I'm assuming that everyone is able to see the screen and listen me clearly. If not, notify me. Okay. Uh, so uh, remember last time in our lecture and also in your labs, you have written some instructions, some assembly instructions in in your programs, both in lab 1 and lab 2. And so the question becomes like, okay, as human beings, we are writing the code we are writing the code in assembly. But for example, if we are specifying, okay, add, let me again to register RD and RR. So which is basically destination. This one is first one is destination register and this one is source register. So how does, and then let's say I'm writing another instruction where I say, okay, and to register and RD and RR. So how does the hardware knows what type of operation needs to be performed? The thing is like when we write the code in assembly language and then we convert it into the machine code, then each instruction is replaced by a binary code, right? So for example, in case of add, uh, we replace it with we replace it using this template, right? Where we have opcode and then operand. So opcode is like the most significant bits. They are used to specify the opcode, and then the other remaining bits they are used to specify the operand. Now, what is the job of the opcode? So it is basically opcode stands for operation code. So it tells the decoder like what kind of operation this instruction wants me to perform. Remember in our previous slide, here we said that we are using the instruction decoder, right? And now all different kind of instructions, they are fed into the instruction decoder. Now, how does instruction decoder knows that whether a given instruction wants me to perform add operation or AND operation or some other operation, or it wants me to read data from memory or write data into memory? How does instruction decoder knows this? It first looks at the sorry, I think the simulation is again started. Okay, so it first looks at the opcode bits of the these bits of the instruction, and these opcode bits of each instruction, they are unique. So if like let's say the opcode bits are I'm reading from the most significant bit 0, 0, 0, 0 and 1, 1. So it means decoder understand, it identifies that this instruction is an add instruction. So I need to so the add operation is needed to be performed. But then if add operation needed to be performed, then it's mean we also need the operand on what uh, data objects we are going to perform the operation. So in this instruction, for example, when we say add RD and RR, so we also need to have field in the machine code or the uh, binary form of the instruction. We need to have some bits which are reserved to specify these registers. So, and how these bits are assigned. So this bit, the bit, if I read from, okay, let's read from like B0, like this is B0. So B3, B4, B7, B8, and B9. So B9 is reserved. B9 and B0 to B3, they are used together to make, they are used together to specify the source register, RR. And then the bits from B4 to B8, they are used to specify the destination register. Okay. So, but this template is only for add instruction. So for example, if you go to the AND instruction or some other instruction, they may use the similar template, but at least the opcode will be different. And other some instructions, even the template will be different. Okay. So this is the like for only for add instruction. So here you have opcode for add, and then the next, then you have 5 bits to specify destination registers and 5 bit to specify uh, your source register. Remember that add instruction, it can take as input any of those 32 general, there are actually 32 general purpose registers in the AVR microcontroller. So if we have 32 general purpose register, how many bits we need to specify? We need 5 bits, right? How? Because 2 raised to power 5 is what? 32. So it's mean we need 5 bits to specify or to address 32 different registers. So that's why we have 5 bits for destination register and 5 bits for source register. Okay. So here are some operation codes which are like written, but only opcode. We don't have, like, for example, if you want to load data from X, uh, from register X into A, then the opcode maybe is this one. If you want to load data from memory location at address A X into a register, so you are loading data from memory into a register, then the opcode is 1. If you are going to do the another operation where you are moving the data from A minus register, so actually what you are doing is that do the subtract operation and so on. Okay, so these are the different opcodes. When we will study other instructions, we will have a look also at their opcodes. Okay, any questions? Mm, okay. If no questions, then let's move to the next slide where we are going to talk about two different kind of architecture. So like two different kind of architecture design uh, in the sense of how memory is connected with CPU, right? So one is known as von Neumann or Princeton architecture. The basic idea here is the basic feature of this architecture is like we have a single data bus, address bus, and control bus, which connects CPU with both code memory and data memory. Remember that in from code memory, CPU can only read the data. So code memory is only read only. While data memory, it is both read. You can CPU can read and write data to data memory. That's why you have here bidirectional bus. Okay, but in case of code memory, you have unidirectional bus, right? But the basic point here is that uh, both code memory and data memory, they share all 3 buses which connect them with the CPU. Now, the issue with this approach is the problem with this approach is like since you are sharing the bus for for transferring the data from memory to the CPU, it's mean there is a contention, which basically mean that CPU can perform only one job at a time. For example, if CPU want to read an instruction from the code memory, so at the same time it cannot read data from the data memory, or it cannot write the data to the data memory at the same time, because the buses are used at a given time to read data from the code memory, and because they are occupied, they cannot be used for reading or writing data to the data memory, right? Which basically mean that it slows down the it slows down the performance. So now CPU cannot do the two things at the same time, right? So as compared to this, so this approach is simple and slow. Why it is simple and slow? Because you need lesser number of buses because they are shared. But the problem is that the approach is slow, as I explained, that there is competition or there is contention for the bus, and CPU must use bus at a time only for one job, either to read or write data to the data memory or to read from the code memory. Compared to this, we have Harvard architecture, where unlike the Princeton architecture, we have separate data bus, address bus, and control bus for both code memory and data memory. So, which basically now means that the CPU, it can have, how to say, uh, it can actually, for example, if it wants to read an instruction from the code memory and want to write data to the data memory at the same time, it can do that. Why? Because buses are not shared. So it has separate address bus, data bus, and control bus for code memory, and separate data bus, control bus, and address bus for data memory. So there, the CPU doesn't need to wait, right? Because separate buses are available. Okay. Uh, another point which I actually skipped about Princeton architecture is why it is slow, because uh, whenever now if we assume that our code memory, data memory, and CPU, if these are three separate chips, like let's say this is chip 1, this is chip 2, and this is chip 3. So these are three separate chips. If we assume that, if we assume that it is the case, then it's mean that our buses, they are crossing the chip boundary. So our signals are going from, let's say, chip 3 to chip 2, or from chip 3 to chip 1, which basically mean that our signals are uh, traveling across the chip boundaries. Remember, always whenever we need to transfer the signals out of a chip, and then whenever we receive the signals from outside of the chip, it is super slow as compared to the communication on chip, right? So now if we again apply the same assumption here, that code memory and data memory and CPU, they are separate chips, so again the communication will be slow. But the thing is that this Harvard architecture, yes, it is fast because it can do two things at the same time. It can read code memory and data memory at the same time, but also it is typically used in the microcontroller devices or embedded systems, because in microcontrollers we have everything on a single chip. We have CPU, data memory, code memory, all three components on the same chip. So we are not crossing the chip boundary, and as a result, communication is not expensive. So its latency is not high. However, uh, this approach is used mainly in your architectures or in your processors, in your designs, where you have laptop or desktops or uh, other server grade computers. So basically you have, why you do that? Because uh, you cannot put a lot of, for example, let's say you cannot put 16 gigabyte of memory on a single CPU on the same chip with the CPU. So you need lot higher capacity for the memory, and that higher capacity cannot be put on the CPU, so you cannot use this architecture. So you have to use this Princeton architecture, because you have to have a separate memory chip due to the larger uh, memory capacity which is typically needed by the applications or the workloads running on your desktops or your desktop or laptop computers. But as compared to that, the programs which you run on your embedded systems, they are much smaller in size and they consume much less amount of data, and hence you can put everything like core memory, data memory, and CPU on the same chip, and hence you can take advantage of the Harvard architecture. So if you say that, okay, I want to also use how to say Harvard architecture on your laptop, so it will not be possible, because then you will need to put code memory, data memory, and CPU on the same chip, which means that the size of the chip will become too big, and then it will consume too much power, and will become warm, and you will need an extra cooling system. So that's why This approach is normally not used in the embedded systems or in the microcontrollers, Princeton approach. Any questions? Okay, if no questions, then let me move to our next set of slides. Uh, actually, uh, okay, so let me. Yeah, again, I'm assuming that everyone can see the slides. If not, notify me. Okay. Uh, so this slide says introduction to assembly, but title is not fully true in the sense that we have already started talking about assembly instructions in previous lectures, and you have also seen some assembly instructions in your labs, both lab 1 and lab 2. Okay. So uh, so we have seen these slides. Okay, no, not completely. So, yeah. So, what we are going to actually do in this set of slide is focus on the assembly instructions instead of the hardware components. So that we can see how we can perform different kind of arithmetic and logic operations. We will also have a look at the 32 general purpose registers. Remember that I don't know whether I explained it earlier categorically or not, but in your AVR microcontroller 328P, we have 32 general purpose registers which are named from R0 to R31. And when we say them as general purpose registers, it means that we use them to hold the data. And then our instructions, they perform the operations on that data. Uh, PC register, we discussed about it last time, that it is the register which actually holds the address of the next instruction which will be executed in the sequence. And PC stands for program counter. Okay. Uh, Besides an AVR, beside having an ALU, general purpose register, and PCC, it also have status registers, which are also status register, which we'll talk about, and instruction decoder. And there are also some other registers which are known as special function registers. We will also cover them in not today, but in some other lecture. Okay. So let's first talk about our first instruction, which is load immediate. Uh, I think you have used this instruction in first lab and also in the lab 2. Uh, the job of this instruction is to put an immediate value in a register. So here you can, here K is your, let me select the pointer. So K is the immediate value which you want to put in a register, and RD is the name of the register in which you want to put the value. Okay. And this is the name of the instruction, or which is also known as called as mnemonic. So this is the name of the instruction. And here this is the restriction on the on the registers which you can use with this instruction. So which basically mean that you can use this instruction to put an immediate value in the registers from R16 to R31. You cannot use here R0 or R1. Okay. So it's equivalent in high level language of saying that put K in RD, or actually sometimes you can also indicate it as RD, and then you can put an arrow to say that move the value of K into the register RD. Okay. So here are some examples. So when you are saying load immediate 53 into R16, always remember that first you will specify the destination in all instructions, and anything after the comma, it will be the source. So source can be an immediate number, for example in load immediate instruction, or in summary instruction the source will be a register, or it will be a memory location. Okay. So here we are basically saying put the value of 53 in register R16. And now since we are not specifying any symbol, so it's mean that 53 is the decimal value, right? And here we are saying, okay, put the value of 132 in register R19. And here we are, and again, this is decimal value. And in the next instruction, we are saying put the value of 0x27, hexadecimal 27 in register R23. Okay. Okay, there are some other instructions which we can use for performing arithmetic and logic instructions. For example, we have already seen add both in the lecture slides and also in the labs. You have subtract, multiply, and also other instructions which are not covered in this set of slides. So basically, what you can do is that okay. Yeah, someone asked a question, why is there a restriction on which registers I can use for an operation? There are two parts of answer to this question. First, uh, because the way any designer of a microcontroller processor or a microprocessor, they make some decision. Like, for example, which registers can be used with a particular instruction. So without discussing the reason behind that decision, let's say if I have made the decision, then I will design my hardware accordingly. So if I design my hardware accordingly, according to that decision, then it means that uh, when I design the assembly language or the assembly instruction for accessing those registers and for performing the operation, I need to uh, be consistent, and I need to follow those decisions which I have made already, right? Now the second part of the answer, like for example, why we even make such kind of decision, or why they made the designer of AVR microcontroller, they made this kind of decision that okay, the only these 16 registers can be used with load immediate. I am not 100% sure on that, but I have an explanation for that, which is like I think we can get the information about that by looking at the opcode of the load I instruction. So let's try to do that right now. Uh, I can try to go to the book, and if you go to Appendix A of the book, I think they have Appendix A or Appendix B, I guess. They have opcodes for all the instructions. So here, for example, no, but here they explain the semantics of the instruction, not the opcode. Uh, yeah. Again, but I'm not sure, but my guess is that let me go back to the slides. So my guess is that this is because of the fact that the opcode that they have assigned to, let me go back. Yeah, the opcode that they have assigned to load I and is has such a value that when you combine it with the registers, it cannot fit into 32 bits. No, into cannot fit in 16 bits. So why I'm saying this? Because all instructions, or most of instructions, not all instructions, most of the instructions in AVR microcontroller are 16-bit, right? And they prefer to deviate from size, this 16-bit size, and they prefer not to deviate from this 16-bit size as much as possible, right? So why? Because then this has some advantages when you are designing the hardware. Now if you have 16-bit, so it's mean like if you want to specify, let's say register, if you want to allow the registers from 0 to 31, not from 16 to 31, but you want to allow registers from 0 to 31, then you need 5 bits uh, for the uh, RD, and then you also need some bits to the value of K, right? So, and then you some need some bits from for LDI, the opcode of the LDI. Now, I am not sure what is the range, allowed range for this one, for K, right? So if that range and the size they together take the number of bits, and LDR take number of bits such that it becomes greater than 16 bit, then you cannot allow all the 16 bits, all the 31 registers. And that is my like guess that they have reduced it from 0 to 3, which basically means you have 4 bits to specify the registers, and then the remaining bits are used to specify the range of the value, immediate number which you want to put, and the opcode of the LDI. Because if you increase the register, the range will reduce. So because you have limited bits, right? So again, but this is my guess. I am not 100% sure on that. We need to check what is the range of the value which can be put in the value in the register. I know I haven't answered your question completely, but I don't want to feed you any wrong information. Okay. Uh, okay. Instructions. Yeah. So say there are some other instructions which we can use for arithmetic and logic operations, like add, subtract, multiply, and. But then these are not the only instruction. When you go to the book and look at the appendix, you can find the complete list of the instructions which we can perform on the AVR microcontroller, and that also include other arithmetic and logic instructions as well. And maybe we will cover some of them in the lab or in the remaining part of the course. Okay. So let's have a look at them one by one. So for add instruction, what you basically do is like it's straightforward. What you are doing basically, you are saying I want to add the value of the destination register and the source register to get register together, and that put result back in the destination register. So here is an example. So again, first always you have mnemonic, and then you have the destination, and then you have source. So here you are saying add R25 R9. So what will happen is that the value of R25 and R9 will be added together and then put back in the destination register, which is R25. Okay. Again here R17 and R13, add it and put the result back in R17. Uh, I think that in case of add, there is no such restriction. Yeah, actually, I'm sure there is no such restriction. You can use all the registers R0 to R31 like as a source or as a destination. Any one of them. Okay, now let's look at an example where we write a simple program to calculate the number 19 plus 95, right? So if we want to do that, so we need to first put the value of 19 in one register and 95 in another register. How can we do that? By using our first instruction, which we had a look, by using load immediate. So putting 19 in R16, then load immediate 95 into R20. So we'll put this value into R20, and then we can say, okay, add both registers R16 and R20. So R16 will have the result of our addition. Okay. Okay, write a program that calculates 19 plus 95 plus 5. Okay, you have 1 minute. Do this exercise. Do this exercise, and when you are done, let me know. Okay, good. Let's wait for some more people. Finished. Okay. Okay. So again, it's straightforward. You first load these immediate values into three different registers. Actually, if you want, you can also use two registers, but to keep things simple, you can use three different registers. You can load 19 into R16. You are loading a 95 into R20, and you are loading 5 into R21. And then you are saying, okay, add R16 and R20. So now you have result of the addition of 19 plus 95 in R16. And then you are saying add R20 to R16. Now you have the result of overall addition in R16. Okay. So this is the case where you are like using two registers. So first you are saying, okay, load 19 in R16, 95 in R20, and then add them together. So now you have a partial result. So you have done this one, right? So you have this result in R16, and then you are saying, okay, load 5 in R20. So you are actually reusing the same register, right? So you are, it will override the value, R20 will have 5. And then you are saying, okay, now add R16 with R20. So now R16 will get the overall result for adding all three numbers. Okay. So basically you have here saved one instruction. So which means you are doing the things more quickly because you are executing less instructions but doing the same thing. Okay. Again, sub instruction. So it has the same similar syntax as add instruction. The only difference is that you, instead of using the mnemonic of add or the name of add, you are using sub. Otherwise, the things are same. This is your destination register. This is your source register, and the result will be in the destination register. And RD and RS can be any of the 32 registers, like R0 to R31. And this instruction, it affects your status register. We will talk about status register later, uh, but I think if I'm not wrong, your add instruction also affects your status register. So when we'll cover the status register, it will become clear whether add instruction affects it or not. But I am pretty sure that it also affects the content of, if you do add operation uh, on like any two registers, so it can potentially affect the content of status register. How, we will talk about it later. Okay. And also how sub affects the state content of the state register, status register, we will talk about it later. So how, again, things are straightforward. When you say sub R25 R9, so you subtract R9 from R25, and the result is put back in the R25. Again, same here, sub R17 R30 mean subtract the content of R30 register from R17 and put the result back in R17. Okay. Uh, Next, we have another arithmetic instruction, increment. The difference from add or sub is in the sense, definitely one difference is that it, in terms of operation it performs. So it increments the content of the destination register. Note that here we don't have source register because this instruction operates on a single register. So whatever RD register is, whatever content it has, it is incremented by one, and then the result is again saved back in the same register, right? So we don't need a separate source register because it doesn't make sense. So for example, if you say increment R25, so what the effect will be that current content of R25 will be incremented by one, and the result will be placed back in R25. Uh, Like increment, we also have a decremented instruction which does the opposite of increment, where it reduces the value of a register by one. So for example, if you are saying decrement R23, so the current value will be decremented by one, and the result will be placed back in the R23. Okay. And so this is again machine code for increment instruction. And here you can see that like operand bits which specify your RD register take 5 bits, and all other remaining bits are used for opcode. This is an example of example to show that all the instructions in the AVR microcontroller, they do not necessarily follow the same template for opcode. for their machine code. For example, when we had a look at the, where was it? Okay, it was in the previous set of slide when we had a look at the instruction for add and its opcode. So opcode was like 5-bit or no. So 5-bit was registers, destination register, 5 bits for a source register, and all other remaining bits. So you can do the sub math. So it is 16 minus 10 is 6. So 6 bits were used for opcode. But here we are using, I don't want to count, but 50 or 16 minus 5, 11 bits for opcode. So all the instructions, they do not use the same template for their machine code, or they do not follow the same instruction format. Okay. However, majority of the instructions, and when I say majority, it's been big majority of the instructions in AVR microcontroller, they are 16-bit in size. There are some instructions which are 32-bit in size, but we will talk about them later. But most of the instructions are 16-bit wide. For example, increment is also 16-bit wide, and so is the add or subtract, increment, decrement. Okay. Any questions until this point? Okay. I'm unsure if this was mentioned, that is it possible to change the amount of increment, decrement, or is it only by one? No, it is only by one. So if you say increment R1, for example, let me go back. For example, and if you are saying increment R25, so you don't specify the amount by which you need to uh, increment the value. Actually, you cannot specify. It is not allowed. You cannot. So it will always be increment by only one. But if you want to, let's say, increment by 2, so then you need to have two instructions. You need to say increment R25 and then another instruction which says increment R25. Or you can say add R25 and then another register which holds the value of, let's say, 2. Okay, you are welcome. Okay, so address range. Uh, so the addresses which um, should I go to one note or not? Uh, Okay, let me go to OneNote. Okay, so uh, this is lecture V2 day 2, right? Okay, so just give me 1 minute. Somehow my drawing pad is not working, so I think I need to go back to set of slides so that I can draw there. I will look at it why it is not working later. Okay, so uh, so let's say this is your CPU and it generates addresses, right? So it generates addresses. I'm just writing A for addresses, okay? But if it generates the addresses, so these addresses are used not only to access your memory, but they are also used to access the registers. Why? They are used to access the registers, where you can say that You can ask the question that registers are on the chip. And same is the case with the memory, right? They are also on the chip. But then why we need the addresses for registers? Because when you are writing a code, when you are writing an instruction like add, and then you say, uh, let's say R1 and R2, right? So how does, like, R1 and R2 are for our understanding, right? As human beings, but computer doesn't understand what is R1 and R2 or even add. That's why we can need to convert it into the machine code, right? So which means that we need to know the location of these registers, right? So that's why we use 5 bits to specify R1 and 5 bit to specify R2, right? So if we are doing that, then it's mean that then we can convert those, we can treat those bit values as register as addresses, and then based on the value of that address, we can find, okay, if this address is meant for register, or if a register R1 or register R2 or something else, right? So the whole address range, which is generated by the for the data memory in AVR microcontroller 328P, it is divided into different sections, right? So the addresses from starting from all zeros, 4 zeros to 001F, they are used for general purpose registers. If there is any address, memory address, so remember, data we can hold it not only in the data memory, but what we do actually, that after reading the data from the data memory, we also put it in registers, right? So registers are also actually data holders, but just like memory, the only difference is that memory is bigger in size, right? So that's why we also need addresses to access the registers. So we divide the addresses in the range, we use the addresses in the range 4 zeros to 001F for registers, and then the addresses in the range from 0020 to 005F, they are used for IO registers. These are known as, first 32 registers are known as general purpose registers. Next, these 64 IO registers, they are special function registers, and we will talk about them later. Like, we have separate lectures dealing with these special function registers or IO registers. But for the time being, you just need to keep in mind that how to say, all of those registers, they also have their own unique address, just like these 32 registers. Then registers 060 to 00F, these addresses are used to address the extended IO registers. So what is the difference between extended IO registers? So your standard AVR microcontroller, traditional AVR microcontroller, they have 64 IO registers. Like for all of AVR microcontroller 328P, they will have 64 IO register. But there are some versions of the microcontroller which have 160 IO register. What is the advantage? More IO registers you have, it means that more input output devices you can interface, you can connect with your microcontroller. Okay. Uh, so if you want to do that, then you need more registers, and then which means that you also need uh, an address range for those extended IO registers as well. Then the addresses in the range from 0100 to 08FF, they are used to address the locations in your static RAM. So your static RAM is 2048 cross 8, which means what? Which means that it has 2048 locations, and each location is 8-bit wide. So in each location, you can store 1 byte. Okay. So now what does it mean? It means like the register R0 has address 0x00R0. Okay. And your register R31 has address 00x0x001F, right? Even when you are writing, we will see examples, but when you are writing your assembly instructions, sometime you can even write the address of the registers in place of their names, but it will do the same thing. If you write the name of the register, the code becomes more readable. But let's say if you write the address in place of those registers, the name of those registers, the instruction will do exactly the same thing. So how the CPU is then connected with different type of data holders. So which basically mean how it is connected with RAM, your EPROM, which is your code memory, your timers, your general purpose registers. So the same data bus is used to interact with all of them, with all the IO devices, timers, interrupt unit, data memory, and even with your general purpose registers, which are inside the CPU. However, you have a separate program bus to talk with the code memory. Okay, because remember, AVR microcontroller uses your Harvard architecture, where you have separate buses for the data and the code. Sorry, I was wrong if I said this was code memory. It's not the code memory, because code memory doesn't share the address bus or data bus with the data memory. So this is basically the same table which we discussed in the previous slide. Okay. Let's have a look at another instruction which is load direct from data space. We have covered this instruction in lab 2. Uh, Here the thing is, like, in the load immediate instruction, what we were doing, we were specifying the value, the absolute value which we wanted to put in the register. But what if we want to put in a register a value which is currently located in memory? So we want to read a value from memory and put it in the register. So for that, we cannot use the load immediate instruction. For that, we must use load direct from data space, this instruction, LDS. Okay. Again, the first operand before the comma is your destination, and the second one is source. So, but here it is the address of the source in memory. Okay. So it is memory address from where your data will be read and then placed in the destination register. For example, if you say LDS R10X60, what does it mean? So remember, here we said that 32 first generation 32 purpose register, they use the address from range 000 to 001F, right? So these are 32 purpose general purpose register, and then here the range is starting for 64 IO registers, and 0060 is your extended IO register. So you are basically saying read a value from this extended IO register which has address of 0060 into the R1. Uh, we have, just like we have LDS to read the data from the memory into a register, we also have an instruction that actually stores the data from a register into the memory location, and this is called store direct to the data space, or STS. Okay, again, first operand is your destination, but this time it is an address, a memory address. And but remember that all the addresses which we use in these both of these instructions, LDS and STS, they are the data addresses, so they will always be within this range. They will always be within this range, which basically, because we cannot write, or our program cannot read data from the instruction memory. Okay, CPU can read data from the instruction memory, but we cannot write an instruction to read another instruction from the instruction memory. I don't know if it makes sense, or if I'm trying to, if I'm capable of like explaining it. But what I'm trying to say is, like, here actually already we have the figure. So here what happened is that you put your program here, right? When you burn your program using Arduino IDE, the binary code of the program goes here, and then CPU reads the instruction from here one by one and then executes them, right? But let's say if it reads an instruction which says load the data from code memory into the register, so this is not allowed. You can only load data from the data memory into a register. Okay. I mean, logically, it should not be allowed. And I am like pretty sure that it is not allowed. To confirm, what you can do is maybe in lab, you can write an instruction which tries to read from an address of the code memory. You can write this, you can have this instruction LDS read, and here specify an address which is not in the range of the data memory but in the range of the code memory, and then see what happens. Okay. uh Yeah, so this instruction actually stores the data. So what will happen that your value, whatever you have in the RD register, it will be stored into the memory at this given address. For example, if you say STS 0x60 R15, so the content of the R15 will go to the memory at this address. And how we indicate this? By putting the value within the bracket. So address is always placed in the bracket. So whenever, like in comments, you see that something is placed within the bracket, it's mean that it is a memory address. So here we are saying that the value of ADR is treated in this instruction as a memory address. Okay, so you have 2 minutes to do this exercise, where you need to write a program that stores value of 55 into location 0x80 of RAM. Or actually, I think 1 minute is enough. You have 1 minute to do this exercise. And when done, please let me know. Let me know when you are done, and if you can copy paste your program in the chat box, that will be also good. If you are struggling with that, let me know. I mean, it should be simple, not more than two instructions. Yeah, yeah, good, good. Uh, yeah, okay, nice, nice. Okay, thank you. Now let me show you the slides. So you first put the value immediate value of 55 into a general purpose register, for example R20, and then you use using the LDI instruction, and then you use the STS instruction to write that value from register into the memory at the given address. One of the student has shared the solution where he or she put set STS 0x80 and then comma 55. Remember that with LDS instruction and STS instruction, you cannot use the immediate values. You must use a register here. You cannot use immediate value. Okay, with both LDS and STS. And I will strongly encourage you to go to the appendix of the book I guess it is Appendix A, and at least look at the uh, description of those instructions which we are covering here, because it might be possible that I am some details are not covered in the slides. For example, if there is a restriction on the value of this register, like which registers can be used, R from R0 to R31 or from R16 to R31. Uh, as far as I remember, it is from R0 to R31. But that's why I'm saying, like, to be sure, just go to the appendix and have a look at that. Okay. And by the way, this STS and LDS, they are 32-bit instructions. Somewhere in the lecture slides we will discuss that why they are 32-bit, but they are not 16-bit instructions, unlike most of the other instructions in the AVR assembly. Okay. Okay, now let's do the reverse of what we did earlier. You again have, let's say, 1 minute. Write a program that copies the content of the location 0x80 of RAM into the location 0x81. When you are done, copy paste your result. Okay. Okay. LDS 0x80 into R16. Uh, let me, I don't know if, where is the student? Uh, Kurtis, you have sent me a direct message. I don't know whether you would like it if I said here. Your program is correct, but you need to store it in 0x81, not in 0x80, right? Because that is the requirement of the question. Otherwise, it's fine. Uh, yeah, yeah. Okay, yeah. Most of the students, they have done it correctly. So now let us have a look at the solution. So first you need read the content of the location 0x80, right? And for reading, you are simply first specifying the address using LDS instruction and saying put the value in R20, and then you are using STS instruction, store in the directly in the SRAM, where you say, okay, put the data from R20 into the address at the memory address 0x81. Okay. So most of the students did it correctly. Yeah. 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 Good. Okay. Let's see how much. Okay. Let's stop here. And today you have quiz. It will start in 1 minute. And yeah, go to your Canvas, log into the Canvas and start doing your quiz.